Okay, starting the day off correctly with a rocket launch. Welcome to the Starlink Group 1211 launch coverage here. I am EJ, and I'm attempting to do this a little more professionally, but if you know me. Okay, rockets. Yeah, I'll shut up. Yeah, good call. All right. Really? Sir, can I talk to you for a minute, please, sir? I ain't sure what the sound, sir. I ain't sure what the sound, sir. I ain't sure what the sound, sir. I've lost the bleeps, the sweeps, and the creeps. Hey, Izzy.
Go and throttle up.
Happy 2025. Doing a fish. 913 sub. Is that Peter back with a steel chair? Oh my goodness. Yeah, Balksy, talk is cheap. Talk is cheap.
Stage 1 lock slot is complete.
Oh, there is audio this time. Excellent. Okay, so the strong back is retracted. Stage 1 lock load is complete. We should get stage 2 lock load here in another minute or two. All right, so this is Starlink 1211. It's launching out of 39A down at Kennedy Space Center. What booster is flying today? 1086 on its third flight. Some of those fairings, that pair of fairings have definitely been reused. Pretty good. It's a vibe. It's definitely a vibe. This is a 31-day turnaround. That booster flew a year ago. Okay, there we go. This is the fourth launch attempt of 2025. Third Falcon 9 launch for 2025 here. The payload is 21 Starlink V2 minis heading to low Earth orbit. This is the 421st
Gas closeouts.
Falcon 9. Stage 2 lock load is complete. Gas closeout is happening on the transporter erector right there. What they're doing is evacuating the propellants out of the TE to make sure that the liquid oxygen in RP1 is not inside of the launch pad when the vehicle goes to launch. You want your fuel and oxygen inside of the vehicle, not outside. The more you know. When the fairings flow more than the core. Can you believe that? All right, Falcon 9 has entered startup. We're T-minus 55 seconds. Should get a go here for the launch director in 20 seconds.
Launch director, go for launch.
There we go. That was less than 20 seconds, but you get the idea. T-minus 30 seconds?
30 seconds.
That's what I said. $20 seconds.
T-minus 15 seconds.
Yeah, Brandon, you're down there. Kissimmee is a little too close, or a little too far for the clouds
10,
today.
9, 8, 7, 6,
5.
4,
Sound suppression
3,
system is
2,
primed.
1.
Ignition.
Lift off. Go Falcon, go Starlink.
Okay. We got a mid-morning launch. Starlink Group 1211. Departing Kennedy Space Center. Heading to low Earth orbit.
Stage 1 propulsion is nominal.
Good call on the propulsion there. Vehicles pitching over and executing a roll program. It looks like a southeast trajectory out of the Cape today.
Power and telemetry nominal.
I can always tell cardinal directions because the pads, 39A and 39B, face perfectly north, south, east, and west.
Supersonic.
So if you see it departing out of the bottom right of the pad, if you're looking down, that's southeast trajectory. Okay. A little bit of low-lying clouds today. But Falcon Flew right above those.
Max Q.
Maximum dynamic pressure, peak aerodynamic compression load induced on the vehicle during the flight. What SpaceX does is throttle the engines down to mitigate those compression loads. Basically, the air is trying to, the air getting built up on the front of the rocket doesn't have any place to go. So it tries to compress the vehicle. You don't want to accordion this thing. That would be bad. There's no crumple zones here, except on the landing legs. You'll see that later. Okay. Flow phenomenon in the gases here indicating a slight radial out burn. So Falcon 9 is kind of flying in this direction, and it's tilting up. It's pitching up. What that's doing, burning, adding a slight radial out component to your burn here, is increasing your apogee height. Basically, they're trying to squeeze, they do that trying to squeeze more performance out of that first stage. If you look, the gases are not uniform coming out of this engine. There's like an open area down here. But as we get towards main engine cutoff, the gases become more symmetrical. That indicates that it's following its prograde velocity vector, basically going in the direction that it's flying.
Main engine
And the reason why it does that is preparation for this.
Stage separation confirmed.
Okay, we got a good separation on the upper stage.
and back ignition.
Good ignition. Beautiful shot of the Florida coast there. That's you can see all the way up to Jacksonville right there. This camera is kind of upside down. North is this way. The clouds seem to be over the southern part of Florida. Now this camera is facing right side up, so you can see all the way to the Gulf of Mexico right there. You can even see a little bit of Tampa there. Stand by for fairing separation.
Fairing separation confirmed.
Good. We got 21 Starlink V2 minis being exposed to space for the first time there. Good separation. Everything looks good here. Pretty dang routine, guys. Knock on wood. Crunch, you're heading to the Cape tomorrow to get on a cruise on Friday. Assuming nothing slips, I'll be there for New Glenn and Falcon 9. Yeah, dude, it's gotten to a point, Crunch, where you're more likely to see a rocket launch at the Cape. I remember when, you go back 10 years ago, it was hit or miss. Like, even if you were down there for a launch, right? Like, okay, I'll give you an example. In December of 2015, I went down there for the first Falcon 9 RTLS, right? The first Falcon 9 RTLS was supposed to launch a week before it actually did. And I ended up spending like a week and a half in Florida. Oh, I know, that sucks, right? But yeah, like that's how it was once upon a time. Nowadays, if I stayed down there for a week and a half, I'd see like 5 rocket launches. It's just... That sounded weird saying that, because this has happened so ridiculously fast that I distinctly remember what it was like when, a rocket launch is happening. Oh my God. No. Now we watch rocket launches while we're sipping our morning coffee, baby. Thoughts on the possibility of Flight 7 slipping in schedule? I think it's going to be next week, Space Wolf. Elon was doing another stream. I think he's playing Path of Exile now. And he said that it's going to delay 3 or 4 days. He's back in my day. Dude, Geresto, I know full and well I'm doing a back in my day. I had to travel up 3 stairs naked or something. Like, dude, I fully understand. Like, that I'm like, am I a rocket boomer? Is this how this happened? Like, what's going on here? But really, like, you're more likely to see a rocket launch coming out of Florida. That's as mundane as seeing a jet take off, like a plane take off in Florida nowadays, which is crazy to me. NSF said net Monday for Starship. I think that's right. Yeah, I couldn't see it. Sad noises. You saw Falcon Heavy from here before. Yeah. Also, shout out to Kissimmee. Kissimmee's a nice place. Very underrated.
Stage 1 FTS.
I like Kissimmee.
Stage 1 entry burn startup.
Another day that ends in Y here in Central Florida. Yeah, baby. Here's the best part. Supersonic retro propulsion. Falcon 9 is firing its engines to slow down, but it's also firing the engines to keep the plasma away from the vehicle. If you look at the gases, how they're propagating on the bottom of the vehicle, it looks like a heat shield, because that's what it is. It's pretty awesome. It's my favorite part. Oh, we got a lot of soot. Got a lot of soot on that camera. Everybody talks about supersonic retropropulsion, but nobody talks about subsonic retropropulsion. That's just the landing burn, dude. We talk about that every time Falcon 9 lands, Graham. What's wrong with you? What people are really not talking about is an exo-atmospheric deceleration burn. If you know, you know. Okay, everything looks just fine here. Oh, whoa, little windy out on the Atlantic today. Falcon 9's being pushed around like a leaf in the wind there, but the grid fins will compensate, steering it right down to its final destination on the drone ship. The drone ship that is catching today is a shortfall of gravitas. Ooh. A lot of vapor accumulation there. Oh yeah, very turbulent air. In SoCal, let's not talk about wind. Okay, be safe, dude, please. Okay, we got a landing burn.
Stage 2 terminal guidance.
Grid fin's doing some work there. Looks a little choppy out on the seas today. Oh yeah, definitely is. No caps though.
Stage 1 landing leg deploy.
Landing legs deploy, grid fins locked. You're on TVC and attitude control. Shut down.
Stage 1 landing confirmed.
Dead center, right in the bullseye. 1086 lives to fly another day. I swear, if they cut the cast before second stage engine cut off again, I'm going to be a little upset. Okay, 27093 staging velocity at 137. Everything looks good there. I do not know, however, I would like it if you're willing to explain. All right, we got a nominal orbit insertion there from SpaceX. Another successful Starlink mission, 21 more Starlink V2 minis going up into space. It includes 13 direct-to-cell satellites, which is pretty cool. Exo-atmospheric retroburn, Dave, is what Blue Origin calls their, or at least what Jeff Bezos called his supersonic retropropulsion. He won't call it supersonic retropropulsion for some reason. He called it an exo-atmospheric deceleration burn. That's what he called it. Yeah. Yeah, no one's talking about it because New Glenn hasn't done that yet. Older Buffalo, what's up, man? On the launch the other day, just after the second stage engine caught off, there were a couple of small but very visible pieces that seemed to fall away from the rocket above the engine itself. Did you see it? I assume it's normal, but wondered what it would be. Oh, yeah. No, that's normal, dude. It's solid oxygen, believe it or not. You're talking about stuff that comes out of this, the vent pipe. Here, let's,
Nominal orbit insertion.
Here, let's back it out a little bit. You're talking about this stuff right here? Solid oxygen. Yeah. So you have a tap-off venting line here. What that is it's a LOX vent line. You can actually see what it's connected, like what that actually, it's a quick disconnect if you really want to know, Older Buffalo. Like here, take a look. See them right there? Now, why? What are those connected into? Well, these are connected into basically a vent line that connects into the Merlin Vacuum's second stage turbine machinery. Now, okay, Older Buffalo, just in case anybody's wondering, like, I'll give you guys hey, WD-40, thanks for the raid. Did you get a good shot today or what, dude? New Glenn does do an entry burn, yes. Exo-atmospheric deceleration burn is what Jeff called it. I'm assuming that Blue's probably told nobody to call it supersonic retropropulsion because that's what SpaceX calls it. Clouded over, splendid. Ah. Well, did we at least see some birds or what? Hey, virtual assistant, what's up? Anyway, Older Buffalo. Yep. Excuse me for 1 second, WD-40 Raiders. I'm talking about turbine machinery. We're nerding out here. Just give me 1 second. Sketty, it's a flocking raid. All right, so Older Buffalo, that's the turbine machinery. Now, what's in the turbine machinery? Well, on the Merlin vacuum engine, you have it's what's called a closed cycle gas generator. I'm trying to get a decent shot with good lighting here. Trying to scrub through. We get to the later parts here. All right. There we go. So take a look. The turbine machinery is right here on the side of the engine. So what is in the turbine machinery? So you have a gas generator, which is a gas generator is basically if it's a jet engine minus the compressor. Okay? So you don't have a compressor. Why do you not have a compressor? There's no air up there. Having an air compressor at the front of your jet engine, your turbojet, is not going to work very well. So don't worry. Falcon 9 brings the liquid oxygen with it, right? Most rockets bring the oxidizer with them. In fact, all of them do, unless somebody's figured out a way to get around that, right? It's closed cycle. It's not a stage cycle, Graham. It's closed cycle. Differences, okay? So, look, the turbine machinery is a gas generator. That gas generator is basically the back half of a turbojet engine. So you have an injector plate, right? You have a little injector plate that shoots liquid oxygen and RP1 into a combustor, and that combustor blows up and it spins a turbine. All right? The exhaust from that goes into this recirculation manifold, which film cools the nozzle. That's why this part of the nozzle is nice and cool, because the exhaust from the jet engine, believe it or not, is cold enough to actually cool it. That's how hot rocket exhaust is. A jet engine exhaust is being used to cool things. Yeah. So what is this jet engine, this half of a jet engine, attached to? Well, the fuel pumps, hence turbo pump, right? Pretty straightforward stuff. The jet engine is spinning impellers that pump fuel into the engine at very, very high quantities, because a jet engine is the only thing that spins fast enough to be able to feed the fuel and oxidizer at the rates that are needed to sustain your combustion. Pretty straightforward stuff, right? Older Buffalo, I'm pretty sure you know all this, but just in case. So what does that have to do with the vent lines? Well, okay. That vent line right there is attached to your liquid oxygen impeller machinery, okay? It's a tap off from that with a little valve that opens and closes, right? Now, why? Well, in the very similar manner that your car engine, right? If you're where I am right now, or pretty much anywhere in the US, it is freaking freezing right now. And if you have a car with an internal combustion engine in it or diesel, you got to get that thing up to temperature. If you're in Canada or in the Midwest, or somewhere where it gets really, really freaking cold, you have a block heater, right? Because the engine doesn't work very well when it's cold. It has to get up to temp, right? It has to get to the right operating temperature. When it's at the right operating temperature, it works better, right? All the seals basically heat up and everything works right. You try to do a cold start on cars, they don't really like it too much, because the engine's not supposed to, internal temperatures in the engine are not supposed to be cold. It's supposed to be hot, because an engine has a lot of explosions going on in it. Explosions are hot. So, okay, what does that have to do? Is the turbine machinery blowing anything up? No. But it has to get to its operating temperature. So what is its operating temperature? Well, that entirely depends on what it's doing. Well, what is it doing? It's moving liquid oxygen into your combustion chamber. Liquid oxygen, especially the densified liquid oxygen that SpaceX is using, is very freaking cold. We're approaching, it's not exactly, but it's almost like minus 200 Celsius. That's cold. That's really cold. The turbine machinery is not designed to operate at ambient temperature. It will not do that. It will not operate at ambient temperature. If you tried to run that turbo pump, it would spin a bearing at ambient temperature. It's designed to run at minus 180 C. at the very least, right? The metal will contract and all your seals will contract when you start putting liquid oxygen into that thing. So, in order to make sure that you don't basically cold start, proverbially, or in this case, hot start your rocket engine, they trickle propellants into the turbine machinery to cool them down, to get the pump to its operating temperature. If we go back to here, right, you could see that the Merlin vacuum, those vent lines are connected to an external vent outside of the interstage. The reason why is because they chill down the engine. They start trickling, Falcon 9 starts trickling propellants into the Merlin vacuum engine way back here to make sure that that engine is primed and ready to go when you have staging like this. That's what those vent lines, those little fingery vent lines are doing there. They're vents for the liquid oxygen to make sure that all components of the turbine machinery on the Merlin vacuum is cooled correctly before they get to the correct operating temperature. So a byproduct of this is you get solid oxygen accumulating on the outsides of those vent lines and basically being dumped overboard, and then get stuck on the recirculator manifold right here. Now, does it solidify because space is cold? No. Space is nothing. It's nothing. There's nothing there. It's the vacuum. So why is it freezing? Well, you have liquid oxygen that's being used to exchange the heat, to pull all the heat out of the turbine machinery, okay? So this is thermodynamics here, right? It's designed to pull all of the heat out of that turbine machinery to get it to the correct operating temperature. If your liquid oxygen is conducting heat when you flow your propellants through your turbine machinery, right? If it's conducting all the heat and getting all the heat out of it, right? You are putting heat into liquid oxygen. So what happens when you heat up a liquid? All right, this is not even thermodynamics. This is 7th grade science. What happens? You get a phase change, right? Your liquid is going to turn to gas. I mean, liquid oxygen already wants to exist as a gas. Heating it up just accelerates that process. So you have gaseous oxygen, or GOX. Yeah, everybody just likes saying GOX. Being shot out of this vent line. So how is it phase changing from, if it was a liquid that was heated up to a gas, how is it phase changing to a solid? Doesn't it need to freeze? So wouldn't space be cold? No. No. There's this, and once again, Older Buffalo, I'm not sure if you know this or not. I'm just giving an explanation, all right? Just in case anybody else wants to know. So you have gas that is being exposed to the vacuum. There's this law that governs how gases work in physics. It's called the ideal gas law, PV equals nRT, okay? What that basically means in non-nerd speak is that when something decompresses, it gets really cold. And when gas gets decompressed, it gets really, really cold. And when gas compresses, it gets really, really hot. That's it. That's all. That's why re-entry heating happens. More or less. Compressed gas creates shock heating to the point where the gas gets so compressed that it rips apart. It ionizes. The molecules actually get ripped apart, and that splitting that molecule creates plasma. Yeah. Compressed gas makes a lot of heat. Now, in this particular case, you have gaseous oxygen at high pressure going to the vacuum. No pressure. Nothing. No pressure, right? So when that gaseous oxygen hits the vacuum, it instantly depressurizes. That small window of depressurization where you're going at, I don't know what the pressure is on that vent. Let's just say it's like 1 bar or something. When you're going from 1 bar to 0, that momentary depressurization, right, before the pressure drops to nothing, causes solidification because the temperature drops because your pressure goes down, right? That's why you get those solid oxygen chunks accumulating on the recirculation manifold right there. Yeah. Yeah, that's totally normal. You can actually see them really well right there, see? Perv nerd. What would the flow rate of the impeller be? I don't know, goalie. We would need, I'm sure we could extrapolate that. Like like how many pounds per square inch is your injector plate on a Merlin 1D? I'm sure you could figure that out, but we're not doing that here. You know, just in case anybody thinks I don't know how to figure that out, you could find that from the exhaust velocity. The exhaust velocity and the total impulse, the specific impulse of your engine is derived from the exhaust velocity and your total impulse of propellants, okay? So from there, you could discern a flow rate, your mass flow rate, your M dot, which is the flow rate of gases through the throat of the nozzle, or through the throat of your engine, right? And from flow rate, you could probably discern injector pressure. So you could if you get the pressure there, you could probably get the flow rate as well. We're not going to do that here though. Oh, the chiller? The chilling mechanism, goalie, relies on residual tank ullage pressure. So in order to get anybody here that if you work in like the oil and gas industry, or if you're a plumber, right? You know what head pressure is. Head pressure is basically creating pressure in the pipe to get liquid to go where you want in the pipe. You got to remember, like, if you think about a pipe, right? Just the pipe that goes to your toilet, all right? There is no directional. There's no, the pipe doesn't know to move water in one direction or another, right? If I had a tube right here and I poured water in one way and I poured water in the other way, the gravity is what's discerning where that water goes. There's no logic behind a pipe where it moves stuff. So what you have to do is you have to create a difference in pressure. Now, how do we do that with the water for your toilet, so to speak? Well, you could have at a water station, you could have a pump that creates head pressure in the pipe. So when you turn the faucet on or flush your toilet, right, it goes to fill the bowl up again, right? Or a much simpler way is have a much smaller pump, elevate the water and use Archimedes' principle, use gravity to create head pressure. Gravity's pushing down on water in a pipe, that creates head pressure. Boom. That's called a water tower, right? If you ever seen a water tower, that's what it does. There's just a little pump at the bottom that moves water up into this thing, and gravity pushes down on it to create head pressure. Now, how does the rocket create head pressure? Where you are, you're under acceleration here, right? So in gravity, you can't really rely on gravity when you're up here to feed your propellants correctly. So, and you're not under acceleration when the rocket engine isn't on. So, like, let's go back to staging here. All right, when you get to staging, how does this engine start? How do you trickle propellants in, right? Well, they use what's called tank ullage. There are helium tanks inside of Falcon 9's fuel tanks. They're what's called a helium bottle. It looks kind of like a scuba tank that's been wrapped in carbon fiber. It's a little more complicated than that, but what these tanks are they carry super chilled helium in Falcon 9's case. And as Falcon 9 drains its fuel tanks, right, these helium tanks open and they pump the cavity where the propellants were, they pump that full of gas. Okay? That's called tank ullage. Now, when the engine isn't on, in this momentary thing right here, or when they're chilling down the engine, they open up pre-valves, right? A smaller set of valves, or it could be your main valves. I mean, it really depends on the design. And the pneumatic pressure, because fluids are not compressible for the most part, and gases are very compressible. If you pump a lot of helium in there and increase your tank ullage pressure, the pneumatic pressure is going to create head pressure. It's going to push those propellants in. It's kind of not a passive system, so to speak, but you have pre-valves that open, or it could be your main valves. It really depends on the design, dude. Some rocket engines just open the main valves and just let the propellant trickle in. That can create some shock heating, but if you have a vent line, it's shock heating your propellants. If you just basically flush the toilet of propellants into your rocket engine, right? You're putting stress on the valves that go to the main injector or wherever, right? It really depends on motor design. Some motors have just one set of valves. That's it. And then everything else goes into the engine, right? Some of them have pre-valves that allow a small amount of liquid oxygen to be trickled in. The flow rate is really low, goalie, but it does depend on the design. I mean, I would assume that the Merlin vacuum probably has pre-valves. I don't know for sure. I'm guessing 100%. Because, okay, I would assume it has a pre-valve because your gaseous oxygen, right? Your gaseous oxygen that flows out of these vent lines right here during chill down that's not a lot. So I would assume a pre-valve is controlling that, because if they had just main valves that opened up during Merlin vacuum chill, right? This pipe, that vent pipe, would be a lot bigger, right? Because what you put in, you got to put out, right? Or they could have main valves and then their vent lines could be a smaller valve, right? Because gas, once again, gas is compressible, liquid isn't. If it turns to gaseous oxygen, it could shoot out at very high velocity here, but you could have a low flow rate going into your turbines. Once again, this is a lot. This is getting into propulsion. Propulsion gets very complicated very fast. The Earth really does look flat from space. Marshal Georgy Zhukov. Hey, try crossing the river upstream more next time. Maybe you won't get 1,000 people killed. Or 100,000 people. The more you know. Could have killed Army Group Center a lot faster if you didn't. Or if you did that. I'm just saying. I'm just saying, bro. I'm just saying. You're going to come in here and try and cook me, I'm going to cook you right back. I don't get it. Don't play that. Sorry, man. What's up? How you doing? I've been playing too much Hearts of Iron, Marshall. I've been playing way too much Hearts of Iron lately. Real armchair general stuff. But yeah, anyway, a little bit on propulsion there, guys. I don't want to get into specific details here because I don't know the specific details of a Merlin vacuum engine because I don't work for SpaceX. But I know how they work. I could get you the general operating principle here, not specific details, though. But yeah, Older Buffalo, see all that? That's solid oxygen accumulation. Now, interesting here, if you want another postscript to this, right? So, you have second stage engine cutoff right here, right? And watch, something very interesting happens here. Watch. Wait for engine shutdown. Now look. Another vent opened. Now here, you want to hear a real kicker? Remember those helium tanks that I told you about that create the head pressure that feed your liquid oxygen? Well, okay, look at those vents right there. Now, what do you notice? No solidification here. A little bit right there. You're getting a little bit of buildup on one of the vent lines right there, but that one isn't. Why no solidification? It's not oxygen. Whenever you shut down a rocket engine, you don't want to leave liquid oxygen or RP1. Well, you could leave RP1 in the lines. That doesn't really matter. You don't want to leave liquid oxygen inside of your turbine machinery. Why? Well, short story, oxygen oxidizes things. That's bad. Oxidizer causes corrosion. It causes rust. Anybody that owns an older vehicle, you know exactly what I'm talking about. I mean, that corrosion, that rust and rot is from sodium chloride. It's from salt, but whatever. You get the idea. You do not want to leave that inside of your rocket engine. Liquid oxygen will rust your rocket engine from the inside out. Yeah, very bad. That's not good for it. That's really not good for it. You don't need rusty bearings inside of your turbine machinery. That would be a big mistake. Right? So that's helium right there. Those ullage tanks have, those helium tanks that are inside have another line that goes down into the turbine machinery. And basically they evacuate the turbine machinery. They get all of the residual liquid oxygen and gaseous oxygen out of that turbine machinery when they shut the engine off. Basically, because if you left it in there, it would rust. Like if Falcon 9 needed to start its engine again in another 15, 20 minutes, and you just left the liquid oxygen in there, you would have a very bad day. You'd go to start it and something would rust. You'd spin a bearing in your turbine machinery. Yes, that's a thing. If you spin a bearing in your turbine machinery, the rocket engine blows up. Just like if you spin a bearing in a car, you're asking to visit Rodney. The more you know, right? So, why are we getting no solidification with our helium here? Well, what's that about? Well, you're getting no solidification here because helium does not like to solidify. Just like hydrogen. Hydrogen and helium are distant cousins on the periodic table. They're similar, but they're not. Helium is a non-reactive inert gas. Hydrogen is a very reactive gas. But they're also very similar. They're both very conductive of heat. Just on a side note, I mean, if anybody cares, that doesn't really have any bearing on this conversation, but whatever. If you didn't know that, now you know. Hydrogen is a great conductor of heat, like copper is a good conductor of electricity. But so is helium. Now, they aren't really necessarily using that here for thermal purposes. The helium, because it's non-reactive and it's inert, you can flood a liquid oxygen impeller here, and you don't have to worry about an explosion happening in there. We know from Rocket Factory Augsburg that having explosions inside of your fuel pump doesn't end well. So they flood the turbine machinery with helium to make sure that it basically preserves that. It gets all the liquid oxygen out. So that's why you see the liquid oxygen, the gaseous oxygen line, a little bit, you get a little bit of solidification here. And then, I mean, there's mixed gaseous oxygen and mixed helium here. Time to wake up. So you get some solidification, but they make sure that the engine is completely purged out before they go to fire it again. The 9 engines on the first stage do the exact same thing. And the engines that they use, the 3 engines that they use, the E1, E5, and E9 engines that they use for supersonic retropropulsion, and then again for the landing burn, yeah, they're cycling them every time. Can you believe that? Ridiculous, right? It's a lot more complicated than just turn the engine on, turn the engine off, turn the engine on, turn the engine off, turn the engine on, turn the engine off. No. So check this out. Right before, if you look close, right before the entry burn, you can see gases coming out of the bottom of the rocket. See them down there? It's only for a split second. But they're doing that exact same thing with the Merlin with the Merlin 1D engines down there.
Discovery, go at throttle up.
That may have been an ACS pulse, but sometimes you can see it, sometimes you really can't. It really depends on the lighting. But they're doing it right there. They chilled down 3 engines, fired 1, and then fired 2 and 3. And that's why the plume changes shape. So that's a single engine right there. And then the outer engines ignite. And see the shape change? That's 3 engines. Right? And now if we get down here, once again, a little bit difficult to see, but if you look down there, you can see gaseous oxygen coming from the bottom of the vehicle down there. It's hard to see because so much crap got on the camera. All this stuff that got on the camera is carbon soot. Remember how I told you the Merlin vacuum engine is closed cycle. The exhaust from the turbine machinery goes into a recirculation manifold that keeps the nozzle cool. The Merlin 1D engines don't have that. They're an open cycle engine. They basically dump the gas generator exhaust overboard. So when the rocket's flying business end first, all of that soot gets shot out and moves up the vehicle and gets tracked all over the camera. That's why Falcon 9, when it lands, is all covered in soot, because it's rolling coal. Older Buffalo gifted 5 subs. Thanks, man. And Caviar had a 50-month resub right there. Big 5-0. Thanks, man. It's hard to see, but you can see the gases down there because they're priming the E9 engine for the landing burn. And then when this thing lands, check it out. When it comes down and lands here, I'm going to move my head out of the way. Well, you see that there's some gas that gets shot out here that's definitely not dirty like this, right? See all that? Purging systems. Same thing. They're purging out the engine. Now, obviously you do that because you want to use your Merlin 1D again. but also you purge it out because shutting off an engine like this when you're coming in for a landing, and SpaceX found this out with JCSat 14 and JCSat 16 back in the day when they were pioneering landings. So if you look, you got to look real close, but down here on the deck of the drone ship, there's some propellant down there. You can see it. When you shut a rocket engine off, when it's back down here, right, you get residual propellant inside of the lines. Basically, remember I told you there's those valves and everything, but when you shut the engine off, you shut those valves, there's some residual inside of your turbine machinery. Now, for the vacuum engine, they use helium to purge that out, right? And that's what they're doing here. But gravity, because now you're back down on the surface, gravity is pushing all that propellant out the bottom of the engine. So engines can burp. I call them engine burps. They burp during shutdown sometimes. And they puke out a little bit of residual atomized propellant. Now, you look down here, I said there was propellants, not liquid oxygen. That's propellant. That's meaning, you shouldn't say propellants, but whatever. That's atomized liquid oxygen and RP1. So that's mixed fuel and oxidizer down here. Now, SpaceX, the reason why I said a call back to JCSat 16 and JCSat 14 is because if you look at those things, the whole bottom of them looks like it burnt to the ground. Because it did. They had problems snuffing the fire out. Yeah, that's why they put FireX systems on the drone ships. And that's why the drone ships also push water out from the deck now. I mean, that was a lot later, but they have FireX systems to basically shoot this thing to put out all the fires on the drone ship, right? Because what happens is all those propellants get coughed up like it's like if you have a garden hose, right? And you have a garden hose like on the side of your house, and you have that attached to a sprinkler, and you shut the hose off. There's still water in the line, so you go to twirler dirler the hose up, and water gets everywhere. Same thing, only it's not water. It's liquid oxygen and RP1, and it can explode very easily because you have mixed propellants down here. Right? It's very easy for it to catch on fire. That's why they go ham with that helium purge right here. So watch, you can see it goes, tss, you see it snuffs out any flames down there. You can see that, once again, the gas has changed. This right here is saturated steam. It's water that they sprayed on the drone ship, and all that water all that water absorbed all the heat from the rocket engine, so it didn't melt the drone ship. If you look at the deck of this thing, they spray it down with water to film cool it, basically. Right? All this kind of darker steam right here is all saturated. That's full of heat. Right? And then you see a different type of smoke come out. It's a lot lighter than this darker smoke. See it right there? That's your purge. They basically snuff out any residual flames at the bottom because you don't want your rocket engines catching on fire when they're not supposed to. Yeah. Now, we'll bring this thing full circle here. Give me 1 second. Let me get some footage for you. So, you want to see something interesting? Here, let's look at the Flight 5 recap video from SpaceX. We want the landing. That's what we're looking for. Now, watch. Also, I still can't believe that this happened. I still can't believe that. Helium is not flammable, friend. It's inert, non-reactive, conductive though. Helium is an inert gas. It does not catch on fire. What's a throttle bucket, Flykin? The reason why they throttle down the engines for maximum dynamic pressure. I'll get to that in a second. They throttle down the engines for max Q, right? Everybody knows this if you've been watching rocket launches. Because you don't want to accordion your launch vehicle, right? Now, how would a throttle down on your engines look on a telemetry graph? So your engines are at full throttle. Now they've throttled back, right? Now they've throttled up past max Q. It looks like a a bucket on the telemetry. That's why they call it a throttle bucket. Thanks. I was thinking of hydrogen. Yeah, friend, hydrogen is very conductive. It's very conductive of heat, just like helium is. Like I said, helium and hydrogen are distant cousins. They're related, but they're not the same, right? But hydrogen is very reactive. Yeah, hydrogen catches on fire or explodes real good. Yeah, it's very efficient. Not very energetic in its explosion, but it's very efficient. It very efficiently burns. Why? Well, hydrogen is very simple. It's just an H. Even if it's liquid hydrogen, which is H2. Very simple chain of molecules, very easy to just blow all of it up. So hydrogen's very efficient, and it burns very efficiently. It's not very energetic, though, comparatively to like a hydrocarbon, for instance. Gasoline explodes a lot better. Hydrogen explodes a lot more efficiently. That's why, like a hydrogen car, very efficient. You get great fuel mileage there because hydrogen is very efficient. But it's not very energetic. That's why you don't see a V8 supercharged hydrogen-powered car. I mean, you could do that. That would be pretty cool, not going to lie. But anyway, now watch. So the booster lands, right? Which still, once again, can't believe that actually happened. Now, see? Look. There's some residual down here. Watch what happens. Or we could just see people cheering. Well, you could see it here pretty effectively. Now if we look at... Come back. You look at this shot of the booster. You see a lot of stuff coming out of the booster. Obviously, that stuff isn't on fire, right? Super Heavy has a fire, basically a fire purging system built into it. In the chines, they have CO2. And they snuff the flames out because you got to remember, you can't spray water on this. It's like 200 feet up in the air, right? You can't spray water on this. I mean, you could, right? But they had that same problem when Super Heavy landed. Same exact thing. Now, why is it on fire on the side? I know someone's going to ask. Why is fire coming out the side? Isn't that not what you want? Well, yeah, you generally don't want that, but you got to remember, Raptors use what's called autogenous pressurization. Now, if you remember, if you've been listening to this conversation, cool. If not, don't worry about it. You remember I said Falcon 9 has helium tanks inside of it, and the helium tanks provide pneumatic pressure to get your propellants to feed correctly. Starship tries to simplify this problem in the same way the space shuttle did. You don't... Cast your mind back to the shuttle. The shuttle has the external tank. You do not want your external tank you don't want to have to fill your external tank with with helium every time. That could get very expensive really quick because helium is a very rare gas. There's not a lot of it in supply here, right? So you have to make the tank as simple as possible. So what does the shuttle engines and Raptor engines do to overcome this problem? Well, there's a gas tap off on the Raptor engines. And gaseous methane and gaseous oxygen go into their respective tanks to create your ullage pressure, okay? That's what these lines going up the side of Super Heavy are for. That's what they're there for. Now, what happens when your engine... Does that mean when your engines are on, there's a possibility of overpressurizing your tanks? Oh, absolutely. That's why they're shooting it out the side. Yeah. So you don't overpressurize the tanks and pop them like a balloon. Got to remember, Super Heavy... 4mm tank wall. The tank wall thickness is that of a coin, almost. 4 mil. That's like that much, maybe. Yeah, that's right. The tanks on that thing are very, very thin. You can overpressurize them, and they will pop like a balloon if you're not careful. So SpaceX, to overcome that problem, when the engines are providing enough gas to get good ullage pressure, they open up the valve on their umbilical. And they're shooting gaseous oxygen and gaseous methane out the side. And what happens is, if you notice, it's atomizing right here, and then it's basically auto-combusting from the residual heat that's being convected off of these down here, those engines that are firing. I don't know if you can tell from the bottom of this, that's pretty hot. This whole area right here is extremely, extremely warm. This whole area. Not here, or like down here so much, but like right there, very warm. That's why the flames are shooting out the side. And that is part of the reason why Super Heavy has a Fire X system built on board. There's CO2 all over the place on this thing. And when the thing comes down and lands, you don't need this whole thing burning to the ground, right? So they snuff out the flames with CO2. There's CO2 inside of COPVs on Super Heavy here. And that basically will extinguish the flame. You could see it being put out right there. Or at least start to be put out. In automotive terms, it's a wastegate. Sure. Yeah, if you want to look at it like that, Gaw. Yeah, absolutely. Hey, I just had a thought. When they shut the engine off, how did they keep it from having a wicked water hammer happen in the lines? They don't. That's what that hyonk noise is when the engine shut off. It's a hydraulic hammer. Yep. You know, the engines turn on and then they shut off and you hear a... Yeah, that's exactly what it sounds like. That hyonk, that's the hydraulic hammer. Yep. It hyonks. Yeah, hyonk. So, once again, after the shot of the crowd cheering, which still bananas to me, it's descending into the heat plume. That's right, friend. See, they snuff out all the flames to make it so the Raptor engines don't catch on fire any more than they already did. Older Ruffalo, that turned into an extremely long response. Hopefully I kept you guys entertained. That was a little bit of a long one. Doesn't Super Heavy use ballast so they have to dump it on landing? Ballast? I've never heard anybody say that it uses any type of ballast ever. Rockets generally don't use ballast at all, Graham, because that's inefficient mass. You get a bad mass fraction if you have to use... if you put more dry mass on your vehicle. I want to hear this yonk you speak of. Oh. I was talking with somebody and they said they kept 50 tons of ballast fuel in the tank. Ballast fuel, not... There's always a little bit... I would not call that ballast. That's just excess fuel. Don't call it that, Graham. That's... No. The ballast fuel is a way to get people to understand why that extra fuel is there, but you shouldn't call it that. It's residual propellant, residual commodities in the vehicle. That's what you should call it, right? So you could definitely see from the ice on this thing that there is some extra fuel. We knew that there was because it took SpaceX all day to get all that fuel out, right? Because your liquid methane and your liquid oxygen are going to boil. Why? They don't like being liquids. Down here on the surface. That's why methane is when you say methane, people think gas. And when you think oxygen, people also think gas, right? Having them in liquid form means they're super cold. And when they're super cold, they're basically the atmosphere, that big thing right there is trying to put heat into this thing to get them to turn into gases again. And you have this problem that you have this problem where, you know, if they boil off, you can blow the tanks because you boil off and create too much pressure, too much pneumatic pressure inside the tank. It'll pop like a balloon. So now you have this booster that's caught on the chopsticks and you can't really get at its umbilicals here because the thing to get at the umbilicals is down there. That's why they kept the thing powered on and kept all the vents open and then put the thing back down on the OLM like a couple hours later to evac the rest of the propellants. Hear about JPL? Mandatory evac of their offices due to fires. JPL might get burned down. Yeah, that's awful. Grav, I know we give people in California a lot of crap, but I wouldn't wish anyone's house to burn down. Not even my worst enemy. Like, that's some lines you don't cross. So, hey, like, we give people from California a lot of crap, but nobody deserves to have their house get burned down. So, please, if you're out there, stay safe. On the flip side, it's just a house. It's just a house. You can replace it. You know what I mean? Not you, Grav. Just get away from the stuff that burns. Take it from somebody that studies fire for a living and how it works and ways to shoot it out of a tube. It's hot. It'll burn you. Don't go near it. Like, I don't think that really needs to be said, but, Flip side of that is that, you know, my heart goes out to anybody out there. No one deserves that. No one deserves that. Anyway, what if life gets you lemons? Get mad. I don't want your damn lemons. What the hell am I supposed to do with these? When life gives you lemons, trade them for whiskey. That's what Derek says. And the other thing is that you always, Grim, you always want a little bit of residual propellants in here, your residual commodities, because you don't ever want to run a rocket engine dry. That would be very bad. You don't ever want to go till you run out of fuel or oxidizer, because the proportions between your liquid fuel and liquid oxidizer, especially if they're both cryogenic, are not ever going to be like perfectly 1-to-1. You might have a moment, like if you're running both the tanks dry, you might have a specific second where your mixture goes full oxidizer rich or full fuel rich. And either one of those is going to cause a big problem. Why does screwing with your mixture cause problems? I'll give you an example. If it goes oxidizer rich, you will create a very energetic fire inside of the rocks. Now, don't get me wrong, Raptor engines are probably okay at tanking this because they can take like 300 bar chamber pressure. But screwing with the mixture could cause the motor to get too hot and introduce a detonation sequence. Or detonation failure mode. So that's called a hard start or a hard stop with rockets. Hard start basically, like I said, is not purposeful induced detonation inside of the combustion chamber. Once again, Raptors are probably really good at dealing with this problem because they can take 300 bar chamber pressure, but all rocket engines, except for the ones that have detonation in the name, all rocket engines at the end of the day are internal combustion engines. They are internal combustion engines, meaning they combust oxidizer and fuel, just like a car engine would, or a jet engine. If you have a combustion engine, you have what's called deflagration, okay? Deflagration is the opposite of detonation. Now, what is the difference between those two things? If you like this kind of stuff, I'm sure you've heard these terms get thrown around, right? What is detonation, deflagration? What is the difference? The difference is how fast the explosion happens. A detonation is an explosion where your initial pressure wave is traveling faster than Mach 1. Detonations are very energetic. My heart goes out again. I don't like using this as an example. The explosion in Beirut a little while back, where somebody decided to store fertilizer in a non-climate controlled building in a hot atmosphere, that's a detonation. That pressure wave was traveling faster than Mach 1, which is why you saw a huge condensation cloud. Another good example would be going back a little further. You go back to 1946, Operation Crossroads. The Baker shot for Operation Crossroads, nuclear, any nuclear weapon is a detonation, but the Baker shot really, really showed it very well because they blew up a nuke underwater. So you saw a lot of condensation in the cloud, so you could see the cloud traveling. Operation Crossroads, the Baker shot is very, like, anytime you, like in a cartoon or a documentary or something, you see a picture of a nuclear detonation, they usually show the Baker shot. You've seen the Baker shot before. Everybody has. If you're even remotely interested in this stuff. Here, this is off Wikipedia, but see what I'm talking about? See the detonation wave? Now, that's a detonation. Now, what's deflagration? A lot of you probably have guessed this. A deflagration is when your pressure wave is traveling subsonic. That's the difference between combustion and detonation. Okay? And keep in mind, this is very basic stuff. I know I can get into more detail about this, but I'm trying to keep it simple because people are trying to learn this, right? PepCon, yeah. The PepCon explosion was a detonation of solid rocket fuel. Yeah. So when you have detonations in rocket engines, that because that pressure wave is moving so fast, right? And it basically shock pressurizes your combustion chamber. If your combustion chamber isn't ready for it, here. Give me 1 second, I'll find it. If it's not ready for it, you get an induced detonation in a hard start and it blows up the rocket engine. That's the simple way of saying that. Here we go. Oh, that's the aftermath. So this is extremely high speed footage of a test engine. This was at a NASA facility a little while back. I don't know how this footage is still up on YouTube, but so you're looking at, I don't know, like 1,000 frames a second here. So this is the rocket engine during startup, right? So the rocket engine is trying to turn on here. Now keep in mind, all this happened about that fast. About as fast as you can snap your fingers. If you watch this, it would just look like it blew up like a grenade. But with the high speed footage here, you can really see this stuff really well. Now this footage is coming from YouTuber Gary Kelly. I don't know where that guy got this footage, but watch. So what happens here, the engine is turning on, your turbo pumps are spooling up, or this could be a pressure fed motor, it doesn't matter. Basically, for a split second here, you have atomized liquid oxygen and liquid methane coming out of your rocket engine. And what happened in this particular scenario is that so this stuff right here, extremely flammable. That's mixed rocket propellant. Very flammable. Don't smoke near it. Because this atomized mixture, the vaporous propellant right here, if there is a source of ignition, it will find it. It's basically, the mixed propellant is designed to blow up really, really, really well, deflagrate really, really well, right? Now, in this particular case, they found the rocket engine found a source of ignition that wasn't the igniter inside of the rocket engine. So watch what happens. Uh-oh. Did you see the detonation wave? Look at what it did. It blew the combustion chamber clean off your injector. That's the top of the combustion chamber. There was enough force in that momentary detonation to separate the rocket engine. Now, I don't know if anybody here knows about flanges. You can see the flange on the combustion chamber here. That usually has a ring of bolts around it on purpose. The bolts are there to, once again, make sure that the flanges are connected together, and it's obviously an airtight thing because you don't want fire coming out of the side of your rocket engine. That is one of the strongest parts of any rocket engine, right there, where your combustion chamber assembly meets your injector plate. That needs to be the strongest part. Look at what the detonation wave did. It blew the combustion chamber clean off. That's why you have residual propellant when you go to turn off your rocket engine, because that can happen during startup and it can also happen during shutdown. Hard starts and hard stops are really bad for rocket engines. I don't know if you could tell by what's going on in this picture. Very bad for it. X-Wing, I got plenty of sleep. Thank you for asking. Now, I know what people are going to ask. I already saw somebody ask it over in YouTube chat. Well, why don't we just make an engine that can... If we make an engine that can detonate, that's a detonation engine, right? We should be able to... you could make a way more efficient rocket engine. Yes. There's a thing about that, though. It's very hard to sustain a constant detonation, okay? It's very easy to combust things and keep the fire going, so to speak, because all a rocket engine does is basically make fire and then shoot it out of a pressurized nozzle. That's all it does. Rocket engines are just shooting fire. It's a flamethrower on steroids. It's like if you took a flamethrower and a pressure washer and kind of combined them into one. Just, I mean, does that mean you can create thrust from a flamethrower? Well, no. That's like a super soaker that's on fire. A rocket engine takes what that thing does and puts it inside of a pressurized environment and then shoots it out the back. That's all rocket engines do. They just make fire and they push it out the back really, really fast. Could you do the same with detonations? No. It's hard to. It's hard to create a sustained detonation like that. Now, that doesn't mean that that can't be done. Okay? Here. So, there are detonation engines around. If anybody is familiar with the German Vengeance Weapon 1, so the V1, the buzz bomb for short, the buzz bomb is using a pulse detonator. So, this thing right here, that thing in the back is a detonator pulse. That's why the thing has the sound that this thing makes is a very low frequency hertz, and it goes. Oh, here, hold up. I gotta, suppress that. It goes, that's what it sounds like. It sounds like a buzz, right? Now, the reason why is because this thing basically just shoots a bunch of detonation waves out the back all at once, but there is a stop in that detonation every once in a while, which is why you hear the pulse. The reason why is because you can't have a constant detonation wave. They move too fast. So they pulse it instead. You pulse the detonation wave, that's called a pulse jet. You pulse the detonation wave and you get constant detonation coming out the back, but it will not totally constant. There's a momentary interruption. Once again, which is why this thing makes a weird noise, right? Now, the reason why you can't get a constant detonation wave coming out is because there's no way to sustain that. That's not the right way of saying it. The right way to say it is basically you try to get a constant detonation wave coming out of an engine, and you try to basically modulate it so the detonation waves are closer to each other, right? Basically, one detonation wave could snuff another one out. So there's no way to get like a constant detonation with a pulse jet. So how did we figure that out? So how do you do this? How do you make a rocket engine? How do you make a rocket engine shoot out detonation waves? Like, how can you do that? Well, this is called an RDE, a rotating detonation engine. So with a pulse jet, you're shooting out detonations at a frequency, usually a very low frequency, right? But you're shooting the detonation waves out basically linearly down a pipe, like what you saw in the buzz bomb, right? With a rotating detonation engine, somebody somewhere came up with the idea of not shooting the detonation waves out straight. They basically swirl them like a tornado. And that's why this thing has a spiked nozzle with an annular combustion chamber. An annular combustion chamber is a combustion chamber that looks like a donut. Right? So that rotating detonation the rotating detonation engine does exactly as the name implies. It's not shooting detonation waves out, it's swirling them around each other. Like DNA almost. It's like a triple helix. They found that if you rotate the detonation waves and you keep them spaced apart efficiently, you can basically create a constant detonation engine. You can actually see a little bit of the swirling going on there. That's mostly shocks, though. That's not like, oh my god, I can see the swirls. Oh my gosh, it's swirling out like a helicopter blade. No. That's shocks because of how the air moves. But these detonation engines they're way more energetic. That is like a near future propulsion that hasn't really gone quote unquote mainstream yet. But yeah, it's possible. You can create detonation engines. Detonation engines are way more efficient. because they make way more energetic explosions. So with the same amount of total impulse, you can actually get a lot more characteristic energy out of that. Basically, meaning if you have a rocket engine and you have a detonation engine, right? And say they, you have the same amount of fuel feeding both of those, you'll get better total impulse out of this. Because the detonation makes a way more quote unquote efficient explosion, I guess is the right way to say that. Yeah. Detonation engines are like sci-fi stuff, dude. If we have rockets with detonation engines, the miles per gallon goes up big time. But detonation engines are also a lot more hard on hardware. It's very rough on the engine. Nuclear RDE? Nobody's made a nuclear rotating detonation engine as far as I can tell. But if you're familiar with Project Orion, at one point there was a nuclear pulse jet spacecraft that was thought up. A nuclear pulse jet. Yep. That's what that is right there. Basically, you don't have a fuel tank, you have a magazine, like a battleship turret magazine or something. And it's full of nuclear warheads, very small nuclear warheads. And basically, it feeds into a barrel, right? And that barrel poops out nuclear warheads. The nuclear warhead detonates right behind the vehicle, and you have basically a gigantic thermal protection system here that's attached to a bunch of shock absorbers. And this thing poops out the nuke blows up, and it pushes this thing up and accelerates the vehicle. Basically a nuclear pulse jet. Yeah, that's Project Orion. They didn't do this because if this thing blows up anywhere near Earth's magnetic field, you're going to have a really bad day. You guys ever seen GoldenEye? Not great. Not great. That. You don't want that near Earth. You don't want that anywhere near Earth. Yeah, yeah. No, not cool idea. Not really the smartest. But yeah, that's a nuclear pulse jet right there. It's very efficient, super efficient, because nuclear detonations are super efficient. I mean, on paper. That has to do with uranium and plutonium's energy density. Once again, we're getting back into total impulse, etc., etc. But all right, cool. I told you there would be nerding out. Anybody that's here from WD-40 is like, how do you protect craft from EMPs?
Go at throttle up.
Electromagnetic pulse, game coder? Well, we're not blowing... There are very strict rules about blowing up nukes in space for a very good reason. The short answer is that the EMP gets stuck in Earth's magnetic field, and you can actually fry somebody's equipment on the other side of the planet because the magnetic field absorbs the EMP and basically distributes it evenly along the magnetic field. They figured that out in the 50s. Not smart. GoldenEye. What GoldenEye does. Yeah. So it's interesting. In the movie GoldenEye, they blow up a nuke in the upper atmosphere, right? Basically in low Earth orbit, right? And when it explodes, it creates an EMP directly below it. Now, that would happen, but what they don't tell you is that would fry a lot of computer systems on the exact opposite side of the planet. Because a lot of the EMP, the pulse that's created from a nuclear detonation, goes in all directions. And it gets absorbed by the ionosphere, and actually it'll get distributed and land on the other side of the planet via the magnetic field. Yeah, they figured that out in the 50s. Not the greatest thing. So if you detonate a nuke, like in GoldenEye, they detonated it over Severnaya, right? Which is, I don't know if that's a real place or not. Anyway, and it blew up everything in Russia. What they don't, I'm telling you, a James Bond movie isn't 100% realistic right now, aren't I? Yep, okay. We already knew that. What would happen in real life is they'd fry something on the other side of the planet, and we would have seen it. Everybody would have seen that. Like they would. There's no way to cover that up, because if you blow up a nuke, basically the EMP travels along the magnetic field and fries stuff on the other side, on the exact opposite side of wherever the explosion was. It's actually super interesting stuff. Yeah. So that you don't want that you don't want a nuclear pulse jet operating anywhere near Earth, at least like that. That would be bad. Now a nuclear RDE, I have no idea how that would work, but yeah. Anyway, the plan for today is to play workers now. Good Northern Lights though. Yeah. Oh, it is a real place. Neat. Severnaya. Northern Land, yes. The movie was inaccurate? Yeah, I know. Fusion Palette RDE. You had a resub there, boss. Yeah, the headset shut off. I didn't hear it. Yeah, see, Kraken, there's a reason why we didn't do a nuclear pulse jet. Buh! 95 is here. Happy buh here. Yippee, my state is on fire again. Okay. With frying stuff, you mean people or what? No. An electromagnetic pulse, Mats, will basically fry anything with an integrated circuit. You basically you're short-circuiting out stuff. Yeah. It would be like taking a computer and putting it near a Tesla coil. A very high-powered Tesla coil. You'd fry stuff because electricity would travel through the air and short everything out. You'd go back to the Stone Age. Yeah, anything not rad-hardened. Mm-hmm. Yeah. You know, electricity likes to take the path of least resistance, right? If you ionize the air around something, the electricity will not go through the lines that you want it to go through. It'll jump. It'll jump through the atmosphere like a bolt of lightning almost. That's why EMP breaks things. Basically short circuits everything. How do you protect electronics from radiation during space travel? Yeah, that was the answer to the question. That's what I was trying to answer. Somebody already asked that. Hey, what do you call a bunch of rabbits hopping backwards? A receding hair line. Okay. Enco with a 79-month resub. An Englishman, a Frenchman, a Spaniard, or German are standing watching a street performer do some excellent juggling. The juggler noticed that the four gentlemen have very poor view, so he stands up on a large wooden box and calls out, "Can you see me now?" Yes, we see ya. Oh, okay. Another reason to get a carbureted car. There you go. EMP proof. I'll check it out in a second, Ordon. So rad shielding stuff, around electronics, you need to basically line them with something. You could use a bunch of different things. Aluminum is a good one. You got to keep in mind that rad hardening electronics means different things because there's different types of radiation rays in space. It's basically a cocktail of radiation fun. It's not just, oh, the Geiger counter's going off, it's going to fry everything. No, there's different types of rays, like radiation rays up there. Alpha, beta, and each one of those requires a different type of rad hardening. It really depends. Where's it going? Do EMPs take out batteries? I don't know, Coltec. Maybe? Probably. It'll short a battery real quick. Should I store my important electronics in my microwave, assuming I remember to turn it off? I would do... no. Solar storms do the same sometimes, right? Yeah, Mats. Yeah,
Discovery,
absolutely.
go and throttle up.
Don't do that, sis. believe it or not, guys, aluminum is pretty good at blocking most radiation. That's why they're, 50 plus years onward, a lot of, well, I was about to say a lot of the Apollo astronauts are still around. The point that I'm trying to make with that is that all of the Apollo astronauts that went to the moon lived long, healthy lives after that, and they didn't come back microwave to all hell. That was a figure of speech. It's not microwaves. I know. Like Charlie Duke's still alive. He was one of the dudes on the later Apollo mission. Same with Jack Schmitt. Both Charlie Duke and Jack Schmitt, they're still alive. They spent a long amount of time on the moon. They spent 3 days on the lunar surface. They're fine. They're totally okay because they were inside of an aluminum spacecraft. Aluminum is very good at blocking a lot of radiation. That's not that people don't understand that. I'm trying to keep this simple. So, with radiation, okay, you have things that absorb radiation, like lead or water, that are good, what's called moderators, right? You don't want to absorb radiation in space. You want to bounce it. You want it to bounce off. So a lot of people say like, oh, let's lead line our spacecraft. No, that's a really bad idea. No, don't do that. One, lead is extremely dense, like me. And two, you don't want to absorb radiation. That'll basically turn your spacecraft into a gigantic microwave that basically nukes anything inside of it. You want to bounce the radiation. Aluminum is very good at that. Now, I know what people are going to say. Well, why do we lead line stuff down here then? You lead line stuff to make sure radiation stays in something. That's what lead and water are good for, like a nuclear reactor. Like let's take a BWR Mark III reactor, okay? It's submerged. The whole thing is submerged in water because water is a good moderator. That keeps the radiation in. You do not want to keep the radiation in a spacecraft. You want to keep it out. So you don't need a moderator. You need something that bounces it. What's good at bouncing? Boron is good at bouncing it. Bouncing radiation off of it. I call it bouncing it off. That's not really the right term. Aluminum is good. Titanium is good to do that. It really depends. Like boron is really good, but boron's hard to make. He said boron. Yeah. Reflection is the word. Thank you, Mihai. Yes. Sorry. Water is a good moderator. It's good at absorbing radiation. You do not want that. That you'll basically contain the radiation inside of the spacecraft. That would be like trying to make a boat out of sponge. It's going to sink. You're not. The whole point of a boat hull is displacement to keep the water out, not in. Boron absorbs, not reflects. Oh, it's not boron. It's beryllium. Excuse me. No. Yes, beryllium is good at reflecting. Boron, you're right. Boron is a moderator. Excuse me. Don't worry about it, Tessa. Lead gets heated by radiation. Radiation particles lose energy in contact with lead atoms. Yeah, there you go. That would be a more technical way of saying it. Buzz Aldrin's still around. Yep. Charlie Duke, Harrison Smith, both 89. Dave Scott is 92. Yep. Beryllium is good at bouncing radiation, but beryllium is probably not what you want to put on your human-rated spacecraft. Yeah, beryllium is very reactive. Yeah, that would be like coating your dirigible with solid rocket propellant and then using hydrogen to pressurize it. Did they try that once? Jim Lovell is still around. Yeah, he's been out of low Earth orbit twice, Dan. That's another good example, yeah. Yeah, they tried that once, using solid rocket propellant for the skin of a dirigible, and then, well, inadvertently using solid rocket propellant, and then pressurizing with hydrogen. It didn't end well. Lead would be a good idea for shielding. I don't think so. Ando, no. You know, I disagree. I would just, I mean, one, you have the mass constraints, like you said. Two, you don't, lead absorbs. You don't want a moderator on your spacecraft. Radiation does not get stored. Yeah, I know. You said it gets converted to heat. Good job. Heat is already a spacecraft's enemy, so now you need a gigantic freaking radiator. So any benefits that you had get pushed to another system. Aluminum is more passive, and it's already most spacecraft are already being built out of that anyway. So once again, why would you do that? It's insignificant. Oh. Where's my lead-lined spacecraft then, bud? I'll, you know. The Hindenburg, yeah, Mats. They basically made the skin out of what we make solid rocket propellant out of, and then pressurized the dirigible with hydrogen. Oops. Fun fact, you know, everybody says, oh, the hydrogen caused the problem. No. One of the generators on board caught on fire. Oops. Well, I mean, how about zinc? It's the only material that Homelander can't see through. Must be good for... All right, I'm switching to workers. That Starlink 1211 launch coverage got a little technical at the end. But, yeah. Hope you guys enjoyed it. I'll be right back. On the YouTube side of things, I'm going to jog the VOD. Twitch, just stay here for a second. We'll switch over to workers and resources. Start building our gigafactory here. Be right back momentarily.